There we go. Okay, so a couple of just quick announcements. One is I've gotten a lot of nice feedback from people in our department and a few people outside of our department on the posters. So well done. They were good posters. I know a lot of people either didn't do them or didn't do them nearly as well as they have in years past. And I thought you guys did a very nice job. The other thing I wanted to mention real quick is I posted it on the Slack channel this morning, but I posted what we're going to look over for the machine learning stuff that we get to talk about for 2 class periods next week. I was hoping we'd get a lot more time with that because it's a deep topic, but we'll start there. And if I remember correctly, it's Cindy and who else is the other person presenting?
I believe it was Sean.
Sean, is it you? Well, Sean may have disappeared. But if it's you, so you two will have to decide how to split that up. It's a rather long document. Don't feel like you need to cover everything, but there are 2 cool examples. One that talks about sort of supervised machine learning and one that talks about classification, so clustering. And I thought those would be particularly interesting things to go over. So we'll do that Tuesday and Thursday next week. The one other reminder is that I'd like you to present your posters in a live group setting during finals week. We are not sure, the department is not sure what's going on with the university final schedule. You'll notice you don't have a final schedule in your student center. Normally, if this were a normal semester and the university didn't tweak the schedule at all, our class's final would be Tuesday from 12 to 2. If that doesn't work for you, please let me know right now if you're here. Is anybody not available Tuesday 12 to 2? I'm going to take that as everybody's great. So I'll send out an email just as a reminder for everybody, but that's the plan. Tuesday, noon to 2 p.m. We'll go through and have the presentations. Okay, with that, I will turn it over to Harmon, who is obviously eager to get started.
Eager to get it over with. Let's see. All right. So Monte Carlo simulations. It goes through this introduction, and it basically says that they're used to model things that are hard in science by using computers to basically use random processes instead of like differential equations to model what's going on. So there's 2 basic problems, I guess. One of them sort of like they're all integration problems. The first one is this area of a circle of diameter d. I think it's the one that we're all like sort of familiar with. You basically, have dots and in a circle and in a square, and then you divide the areas, and you can get pi out of that ratio. This other example, the cone and torus, is sort of the same thing. And then these next 3 examples, they consider like the influence of measurement on the quantity to be determined. So example 60, it basically is about, let's do the reaction rates one, I think. So they reference this one later on. So the reaction rates of the gas mixtures, if you have different a vessel with different molecules. You can determine the composition of the gas after time if you like model the trajectories and stuff. So yeah, and I guess it goes on to talk about the fact that we're going to be using a single random variable, but it's easy to generalize to more variables. And then we go on to talk about how to generate the distributions. It talks a lot about in 5.2.1 about the fact that we don't really have like a random number generator that's perfect, and that everyone has a period of however long. And then it goes on to say that the way you would generate random numbers is using this formula right here. You basically need to set lambda to be much, much bigger than n for the number of, what is n? I think n is just like the, yeah, I don't remember what n is, but basically what you do is they go through here with the formula. They say if you start off with x1, you set lambda to be much, much bigger than n. I think n is the value of the x that you're doing. It's basically what's labeling it. And you do this mod operation where you divide 1, in this case, by 0.7123 times lambda, and the randomness comes out from the fact that we're cutting off the significant digits by the mod operation. It goes on to say that we could have like better stuff if we actually had the computers have like stochastic number generators based on actual stochastic processes. So then it goes on to talk about how we would deal with a uniform distribution and use that uniform distribution to come up with other distributions. So the uniform distribution, it gives the formula for it right here. Between 0 and 1, everything equals 1. You have a correlation plot here. You can see it's like uniformly distributed. There's like no other correlation you see. And then in this other plot down here, it shows the frequency of the numbers. And it looks kind of weird, but the thing that you're supposed to get out of it is that per like parts in 100,000, it's pretty small. The number of times that like the difference between like how many times 0.5 showed up and how many times like 0 showed up, it's like 1,000, but it's like 1,000 of 100,000 is maybe like the sort of like the error, or like how yeah. So then it goes on to say that if you have a monotone function x, or if you have, basically if you're starting off with, if you can generate other single random variable distributions by doing a variable transformation, it gives a formula for that right here. And it sort of makes sense because u of r is just like a constant, so you get r of x back out here. Here it goes through how we would generate the distribution. So what you do is you follow this formula right here. You would go and choose a value of r and see where it falls on here on the x. And from there, you would get the respective, so you choose R, and you look at the distribution, and then the inverse of the distribution function gives you the respective value of the random number X. And then you can see up here on where X falls on, yeah, I'm not getting this part very well. On here. And then it goes on to show how you can do a transformation from the linear distribution to get other distribution functions. And here you think you'd use these formulas right here to get the distribution function you wanted, R of X from F of X. So you just basically integrate F of X, and then you'd invert it to get this function down here. And it goes on showing that for more complicated distribution examples, which I won't go into. I think you get the general idea from the very first one, or at least it's the most clear. Here it shows how to, because the first two ones were just like Cartesian, or the first one was Cartesian, and maybe you needed to be uniform in a angular and circular or spherical distribution. And it goes on to show how to get those functions that you need to do that here. For discrete, because so we just covered continuous distributions. For discrete distributions, it's exactly analogous. And it shows that here it goes over an example where it's the Poisson distribution. And it says that, so if you have some sort of value k and your Poisson distribution has an expected value of 4.6, this function will return the probability of that value. So the summation part here is you summate, there's the bins. The summation of the bins starting from the left, we obtain the distribution function here. And we attach a value k to it, and it makes it so that S is much bigger than R. And the number k follows desired distribution. Yeah, that's as far as I got really understanding what was going on here. The rest of it, I can just basically talk about just the title, basically. So yeah, I don't understand this part, histograms. This goes on to simple rejection sampling.
Yep, it's okay if we don't have to go over all of this. The main point that I wanted you to get at was this idea of how do you generate random data that isn't, I mean, because NumPy will generate random data that looks like a Gaussian or a uniform distribution. How do we generate random data that doesn't look like that? And that's what you were talking about when you're talking about transforming distributions, right? Is this concept that you can use a uniform random distribution to turn into any other thing you want by that game you were talking about where you have the f of x and the u of r and you do the integral relationship. So does that make sense?
Yeah.
Great. So anyway, yeah, good. Thanks. Questions?
So I don't know if there's like really any examples like in the book, but like I guess like when you would want to use like a uniform distribution versus say like a spherical distribution or Gaussian, that kind of situation.
All right. Can somebody give me an example where you would want random points that were uniformly distributed on a sphere versus, say, in a box?
Voids.
Ah,
Would
there
you
you
say,
go.
like,
What was that?
I would say like
Sorry.
in quantum mechanics, or like maybe where the electron is.
Like a quantum particle in a box or sphere.
Yeah, there you go. A hydrogen atom, right? A hydrogen atom is a spherical thing, not a box, right? So you don't necessarily, if you were trying to sample, say, the wave function, you would want to sample uniformly on a sphere rather than uniformly in a box. And maybe an easy one to visualize is, let's say I wanted to pick a random place on the surface of the Earth, right? If I randomly pick a latitude and longitude uniformly, I'm going to pick a lot of places that are near the North and South Pole, and relatively few places near the equator, right? Because latitude and longitude is a way to represent a sphere in a Cartesian coordinate system, right? And so what you're doing is, if you randomly pick a latitude and a longitude, you are going to pick a lot of places around the North and South poles. So you would want to pick, if you were trying to randomly pick a point on the Earth's surface, you'd want to choose your distributions from a spherical distribution rather than a Cartesian one. So, you know, these things pop up. These things pop up a surprising number of times. Okay. So anyway, good job. Well done, Harmon. This book is interesting because the further it goes into the book, the more it really dives into a lot of the particle physics stuff, which is not really what we want to use it for. But obviously, this was written by particle physicists, and they had particle physics students in mind. And so they kind of thought, well, we'll just, teach you all the things you need to know for particle physics as well when we're going through this thing. Okay, so I wanted to give you an example of how you can use some of these random techniques in data analysis. So, we should clap for Harmon. Good job, Harmon. Let me do my little fake clap. There you go, clap. Yay. Okay, so what I wanted to show you here, oh wait, I don't want to do that. I want to do that. Oh, dang it, now please. Okay, let's make you go away for a sec. All right. So usually when we're analyzing data, and it doesn't matter in this case if the data is generated by us as the result of, say, a simulation, or if it's actual data. But the nice thing, if you remember our Monopoly game example, right? We could always get better results by just getting more data, right? We could randomly, instead of randomly generating 100 turns, we could randomly generate 1,000 turns or 10,000 turns or 1 billion turns. And each time we would get, because we had more data, we could do better. Well, in reality, we generally don't have an infinite amount of data. The data is either really hard to get because you have an experiment attached to it, or it's really hard to get because, say, you're trying to run a fluid dynamics simulation, and that sucker is just expensive. So you can't run it 1 billion times. You can run it, I don't know, a small number of times. You can and you can do your analysis, but you don't get infinite data points, right? So the question then is, how do we do some of the things that we did for the Monopoly stuff, and how do we understand what our uncertainties are? So for example, if you remember with the monopoly problem, we were talking about computing moments of the distribution, okay? The thing I want to look at today is how do we know how certain or the uncertainty on those moments of our distribution, right? How do we know how well we know the mean or the standard deviation or the skewedness or the kurtosis or the whatever if we have a limited amount of data? I like to tell my 204A students that you don't know anything unless you know how well you know it. And this is always, my example with this is always when you talk about like Congress is talking about some big bill and they're trying to figure out how much it's going to cost over the next 10 years. And my response is always like, why? I mean, this is the most like ridiculous thing because there are 800 assumptions baked in here. And so what they should say is, oh, this program is going to cost $7 billion plus or minus $12 billion over the next 10 years. Because that would be useful, right? That includes the uncertainty. So how do we know how certain we are in measuring, say, the mean or the standard deviation of some process, right? So we're going to play with that a little bit today. So what I've got here is I've created, I ran our Monopoly script and I did 1,000 rolls or 1,000 turns, right? And then I saved the data. And I can show you over here where I saved the data. I saved the data right here. And I saved it using the save Z command instead of the save TXT. The reason I did that is because save Z saves things as binary files, okay? So think about how a computer stores a number. A computer stores a number as in base 2, right? But it stores it as a number. Okay, so it stores it as, 1.7368247 times 10 to the 6th power, right? Contrast that with how you would store it as text. So as text, each character in the text file is represented by an integer. And that integer can take, I believe, it's 255 values. It may have actually gotten bigger since then because I know that the ASCII tables have expanded. But originally, so if I wanted to store the number 4, I stored it as an integer. Whatever integer corresponded to the number 4 when on the ASCII lookup table. And each character was stored that way. So in order to store my number, 1.76583 times 10 to the 27 power or whatever, I have to store an integer for the first digit, an integer for the decimal point, or an integer for the second, for the third, for the fourth, for the fifth. It's extremely inefficient. So if I save it using save Z, it saves things as in there as numbers, as opposed to saving them as text. The other advantage with save Z is I can put multiple data in the same file, even if they're not the same size of arrays. So in this case, I've saved the number of dice, 2, the number of turns, which is 1,000, and all the results of our rolling, okay? And save Z can, if you save them in this format where you do a keyword, it will actually remember the names of your arrays. And so you can get the names back. You don't have to remember the order they were stored. You can just remember the name, okay? So if I come back over here and I run this thing, I've saved my 1,000 rolls, and I say something like temp equals np.load, and I say print temp.files, it will print out the names of all of the things that are in that saved file. And I can get at them by saying temp.n turns. Or I could say n dice equals temp dot n dice. Or I could say, let's see, what's the other one I had? Oh, dice rolls. Okay, and if I run these things, what did I do wrong? All right, let's pull up the help file. All right. Oh, I see. It's not dot. It's like this. Oh, I deleted everything. It's a dictionary. And now if I look over here in my variable explorer, I've got all my data, right? It's so I have 1,000 rolls of my dice, right? And we can see if we open up the variable explorer that there are my 1,000 dice rolls, right? And if I come over here and just steal my code to plot my PDF, right? Oh, I'm gonna have to, okay, I'm gonna have to grab one other thing. I'm gonna have to make that roll bins thing. So let's see, where'd my roll bins go? There we go. All right, so I rerun the thing and I get a lovely histogram, right? And you can see that this obviously doesn't look quite the same, right? Because I only have 1,000 dice rolls instead of having 400,000 or whatever I had before. But you know, the general idea is still there. So calculating the mean of this thing is easy, right? I would calculate it the exact same way I always calculate things. I just take moments of my distribution. So the same way I calculated the mean here and the variance, I could calculate them over here, right? Oh, what didn't it like? Oh, I have to do this. I'm doing things out of order here. Oh, I see what I'm doing. Okay, hold on. Let me reorder things a little bit. And I want to plot mean move. All right, so now I plot this thing and I say, okay, there's my mean. And you can see that that mean is close, but not exactly what we got when we did a lot more rolls, okay? So the question is, how well do I know that average, right? And that's a different question than asking, what's the standard deviation of the distribution? Because one of them is asking about the width of the distribution, and the other one's asking how certain I am of that mean. Because I know that if I had more data, I would get a slightly different value. But how different? How well do I know it? Okay. And this gets at one of the things that we can do that's nice with random numbers. So what I'm going to do up here is I'm going to import numpy.random as RND. And what I'm going to do, this is called a Markov chain Monte Carlo, or sometimes called bootstrapping. So I need to know how uncertain my mean is. In other words, what I want to know from a statistical standpoint is I want to know the probability distribution function for the mean of my data. Does that make sense?
Yeah.
So what I want, so now this is hard, right? Because I only have one mean, right? The mean is just defined for all my data. So here's what I can do that's kind of clever. I can come down here and I can say, I want to define some n samples, and I want to take it to be the number of turns divided by 2. I still want it to be an integer. Okay. And then what I'm going to do is I'm going to randomly choose some of my data to include. So I am going to say, I'm going to make something called sample indexes that is some random numbers. I want them to be integers. Okay. I'm sorry. I want them to be integers, and I want them to go between 0 and n turns. Okay. And I want the size to be n samples. Okay. So I'm going to randomly pick half of my data. Now here's the fun thing. There's actually going to be repeats in here. I'm going to pick the same data point more than once. That's okay. Doesn't matter. I can pick the same data point more than once. I'm just going to randomly pick half of my data. Okay. And then what I'm going to do is I'm going to recalculate the mean, right? We'll call it mean V2 for the second version. And I'm going to calculate it exactly the same way I did before, right? I'm going to do the sum of roll bins up to but not including the last. Oh, but I don't want all of them, right? I just want half of my data, right? So I'm going to, well, here, let's do it this way. Instead of doing the PDF, I'm going to do it the standard way. I'm just going to do np.sum of roll bins sample indexes. Oh, I'm sorry. I want dice sums. Dice sums, so sample indexes, and I want to divide it by n samples. And when I run this thing, what we'll find is I calculate a new mean. So if I go over to my variable explorer, I see that my mean using all of my data came out to be 8.429. And my mean using half of my data randomly sampled came out to be 8.668. And if I rerun, I'm going to get a different number. And now I got my mean the second time to be 8.45. And now I got it to be 8.11. So what I'm doing is I'm taking my data and I'm using part of it to generate a new mean value. Okay. So guess what read my mind here. What am I going to do next?
Take a lot of samples.
Yeah, do it a bunch of times. So I'm going to come down here and I'm going to put this whole thing in a for loop. I'm going to do it, I don't know, 1,000 times. Okay. And I'm going to run this in range n means. Okay. And I'm just going to come down here and generate random samples. And I'll make an array of means. And so let's see, I need this to be n means long. And then instead of putting it in mean v2, I'm going to put it in means array, location I, right? What are we unhappy about? Nope, maybe we're not unhappy. Oh, I means, that's what I called it. All right, there we go. Now I run this thing, and now what I'm interested in is plotting up a histogram of the means array, okay? So I'm going to start a new figure, which I'm going to call distribution of means. And I'm going to do a histogram of means array. And I think that's probably all I need. I'll normalize it. So density equals true. Okay, and we'll probably need to label stuff. What did it, oh, there we go. All right, now if I run this thing, here's what I get. There's my distribution of means. What does it look like?
Normal.
Oh, let's see, I'm ignoring the chat. Yeah, there you go. Yeah, it looks like a normal distribution, right? Which means if I want to talk about the uncertainty in it, all I need to do is take the standard deviation, right? So I just come over here and I do, I'm going to do the, we'll call it mean standard deviation is going to be, let's see here. It has a standard deviation, right? Is there not a NumPy standard deviation? Let me move stuff out of the way here. Oh, STD is all it is. Okay. Means array. And so if I run this thing, I finally come over here and I see that my mean standard deviation is 0.186. So what I really know here is now I know how well I know the mean. By taking 1,000 rolls, I've gotten a good idea of what kind of variation I'm going to get in the mean if I only look at 500 rolls. Now, there's a limitation here, right? What I've basically said is I know how much the mean is going to vary if I do 500 rolls instead of 1,000. I don't actually know how much it's going to vary if I do 1,000 rolls. To do that, I would need, say, 2,000 rolls, okay? Now, is that 2 a magical number? Well, kind of. The cutting your sample in half is generally sort of statistical best practices, but there's no magic that says that's the only right way to do this. There are you can get into entire things in graduate statistics looking at what happens if you change this a little bit and what happens if how does that vary the true uncertainty that you can't measure other ways. But 2 is sort of a safe rule of thumb. So do you see why this is called bootstrapping?
No.
So everyone's heard the idea of pulling yourself up by your own bootstraps, right? This idea that you yourself lift yourself off the ground. Okay. In some sense, that's what we're doing with the data. We're using our own data to assess the uncertainties in something we measured from our data. Okay. Now, I want to be careful because there's sort of a nomenclature problem here. What we measured is not the standard deviation of the number of spaces moved here. What we measured is how certain we are, or the uncertainty on our measurement of the average number of spaces you would move, right? So the number of spaces you would move is the mean plus or minus the standard deviation. The uncertainty on the mean is what we just calculated, right? So you can use this for anything. Now, why would you use this? Okay. The reason is that this is useful because our data didn't come from a nice, happy statistical distribution that we could just generate more random data from, right? Well, it actually did, but we kind of cheated, right? If this is data, then your data is what you have, right? If let's say this came from, your traveling salesman problem, and you wanted to answer, for this alignment of the planets, our best travel time is this, right? Well, how certain are you of that statement? How certain are you that this is your best travel time? Is there likely to be one that is an order of magnitude better? And you're limited because you can't just sample everything, right? The parameter space is way too big. But what you can do is sample a bunch of random ones, right? And then basically ask, okay, this best one that we found is better than everything else we found by what, right? 10%, order of magnitude, 5 orders of magnitude, right? So we can start to ask ourselves, how confident are we, right? Because if the one you found is better than all the other ones by 3 orders of magnitude, well, that's probably a good sign that there might be another one that's 3 orders of magnitude better than yours floating around out there. But how thoroughly did you study things, and how many did you find, right? These are all the kinds of things that you can address using this kind of a method, where you randomly select some subset of your data, redo the calculation, and get a distribute and repeat over and over again to get a distribution on your value. So does that make sense? All right. So we'll stop there for today. But remember to do have a look at some of that scikit-learn stuff before class on Tuesday. There's a lot there. Machine learning is this whole fancy world, and while we're going to try to give you the very quick overview, there's a lot more than we're going to be able to really go into in detail. So have a look, peruse a little bit, and we'll see how things go. Okay, I think I'm meeting with the Galaxy group right after this. Is that correct?
Yep.
All right. Well, I'm going to turn off the recording. Stop sharing my screen.